Okay, this is going to be a little bitty baby mini lecture on, basically it's going to be on integration. I'm just going to pick up where we left off from the previous mini lecture, which really looked at the chemical shift in a little bit more gory detail. So, picking up where we left off, we were just talking about how these guys are bells and whistles for the aromatic ring. Aromatic ring, aromatic ring. Looking at this more complicated spectrum, what's up with all this blue line stuff? It's kind of messing up my spectrum. What does it mean? Well, those are the integrals, and the integrals are incredibly valuable pieces of information that unfortunately many an O-Chem student has a tendency to ignore. The integral is, as I've mentioned earlier, this distance from here to here. So for each set of peaks, you can see there's an integral trace. I've got a value x here, a value y, z. Guess that's going to be a. That's going to be b. Each one of these distances from bottom to top is going to tell me how many hydrogens are associated with each one of these 1, 2, 3, 4, 5 signals. So how do we make use of integrals? Basically, you got three choices. If you have no idea what you're working with, you don't know the molecular formula, you'll end up getting those measurements in completely arbitrary units, and then you can use the least common denominator approach. So let's say we measured those distances and it turns out there's a ratio of 90 millimeters in height to 36 to 34 to 55. In other words, I have four integrals that are like that tall to like that tall to pretty similar to somewhere in between. And that's a pretty bad drawing, but you get the gist. Alright, what do I do with these numbers? Well, least common denominator, you find the smallest one and divide everything by 34. When you do that, you end up with this set of numbers, which is rather absurd because no molecule in the world is going to have 2.6 hydrogens or 1.6 hydrogens. So what do you do then? Well, you multiply it until you come up with whole numbers. So if I multiply by 2, what do you get? Turns out it looks like this integral for 90 millimeters must be responsible for about 5 hydrogens, 36 about 2, 34 about 2, 55 about 3. Big time fudge factor with integrals. Beware. Integrals are kind of sloppy, so I'd give yourself a good 5% error on your integral calculations. This is not necessarily going to be exactly 5.0. Alright, so that's one way to do it. But if you know the molecular formula, life is much simpler. Because then you know, in this molecule, with my integral measurements, there's 10 hydrogens here. So all I have to do is make a conversion factor. 66 plus 26 plus 40 equals 132. So for 132 total millimeters, there's 10 hydrogens. That makes me find out that for each 13.2 millimeters, that's one hydrogen. So I can take my 66 millimeters, divide it by 13.2, and turns out, well, 5 hydrogens are responsible for this signal. Take my 26, divide it by 13.2. This is 2 hydrogens. 40 divided by 13.2, roughly 3 hydrogens. So now I know that whatever this molecule is, that's a 3 hydrogen signal, that's a 2 hydrogen signal, and this is a 5 hydrogen signal. Hey, 5 hydrogen signal around 7. What do you want to bet? It's probably a monosubstituted aromatic ring, because here are those 5 hydrogens hanging off and showing up around 7. It's amazing how much information you can get from an NMR spectrum. All right, third way to deal with integration is, if all else fails, guess. And this is obviously not something you're going to want to do from the get-go, but as you get better at NMR, it's pretty easy. You're going to recognize that something that shows up around 1, it's not at all unusual for it to be a methyl group. So I'm going to guess that this is around 3 hydrogens. The other thing you're about to learn is that this particular pattern with a 3-line triplet and a 4-line quartet is a dead giveaway for the ethyl group. So you will recognize certain features and be able to take a guess that I think this is probably a CH3. I'm going to guess it's probably a CH3 next to a carbonyl. And I'm going to guess that this is probably this molecule right here. And that this signal is this one. This signal is this one. And this signal is this one. And I'm going to tell you I'm wrong. And I'm going to leave it to you to figure out why that particular molecule doesn't match this NMR. Okay, mini lecture to the max. I've never had a 7-minute lecture. Isn't that grand? So that's all for this one, and the next big dive into the swimming pool will be spin-spin splitting, and so we'll understand these little triplets and quartets. See ya!